Hello, my name is Kevin Craig. I have created 12 modules that cover electronics and measurement for mechatronics. Modern engineering practice requires that engineers model, analyze, and predict before they measure. Mechatronics. What is mechatronics? The diagram you see I created in 1995 as a professor at Rensselaer Polytechnic Institute. It is now used throughout the world to represent the multidisciplinary field we know as mechatronics. Mechatronics is multidisciplinary systems engineering. It is the synergistic integration of physical systems, electronics, controls, and computers through the design process from the very start of the design process. These modules present the fundamentals of electronics and measurement for mechatronics. This is module number 4 on resistor capacitor, RC, networks. The topics are an introduction, the RC low-pass filter, the CR high-pass filter, the RC charging circuit, the RC discharging circuit, the RC circuit square wave response, the RC integrator, the CR differentiator, a first order dynamic system investigation and response, and lastly, the electrical mechanical analogy. Here we see two sets of diagrams. For the resistor capacitor low pass filter, we see the circuit as it behaves at normal frequency. The resistor, the capacitor, the alternating voltage source, the sine wave voltage source. At zero or very low frequency, zero frequency is DC, a capacitor behaves like an open circuit. The reactance is infinite. At high frequency, the capacitor behaves like a short circuit. Its reactance is essentially zero. When we look at the capacitor resistor high pass filter, we see at normal frequency the sine wave voltage source and the capacitor and the resistor. At zero frequency or DC, the capacitor behaves like an open circuit with infinite reactance, and at high frequency, the capacitor behaves like a short circuit with zero reactance. Here we see the resistor capacitor charging circuit. I have a voltage source, a DC voltage source, and when I throw the switch, complete the circuit to the RC circuit, the capacitor will start to charge. This is a curve that shows the voltage across the capacitor as a function of time. And I see what happens at various time increments. Capital T is called the time constant, or normally we use the Greek letter tau for time constant, which is the product of R times C. And at that value of time in seconds, the time constant, the voltage across the capacitor is 63% of its way towards steady state, towards its maximum value, which is the voltage of the voltage supply. And at 5 time constants, the capacitor is essentially fully charged. And the voltage across the capacitor is equal to the supply voltage. This is an exponential curve. The current behaves with an exponentially decreasing curve. At time t equals 0, the current is maximum, equal to the supply voltage divided by the resistance. At the value of time equal to the time constant, R times C, the value of the current is 37% of the maximum value. And at 5 time constants, it's essentially 0. Where do these curves come from? Well, they come from the mathematical analysis of this RC charging circuit. If I apply Kirchhoff's voltage law to this circuit, Kirchhoff's voltage law says that the sum of the voltages around the closed loop is equal to 0. I have a voltage increase equal to the source or supply voltage, a voltage drop across the resistor, and then the voltage drop across the capacitor, which is V sub C. And that's what I write here. The voltage drop across the resistor by Ohm's law is the current times the resistance. But I know the current, which flows through the resistor and then also through the capacitor, although we know that current actually doesn't flow through the capacitor. That current, by the constitutive equation of a capacitor, is equal to the capacitance times the time rate of change of the voltage across the capacitor. I substitute this in for I, bring down the R, and I have now the second equation. This is a differential equation, which upon reorganizing terms, I have this equation. Now, we're not going to be solving differential equations. We let MATLAB and Simulink do that for us, and we transform this equation into an algebraic equation by using the differential operator. D means take the derivative of whatever D is multiplying. So I transform this equation into an algebraic equation by writing it as RC, then capital D times V sub C, plus VC equals VS. This equation. I factor out V sub C, I get this equation. I divide V sub C by V sub S, I get what we call is the transfer function. RC I define as tau, the time constant. And if I were to solve this equation mathematically, the expression I would get is that VC is equal to the supply voltage times the mathematical expression 1 minus E to the exponent minus time divided by the time constant, which is R times C. What's more important than this expression is this curve. The response of this RC circuit to a step input in voltage is a first order response. At tau seconds, the response is 63% of the way to the steady state value, and at 5 time constants, 5 tau, it is at steady state. This is what you need to remember, not the equation, not the solution, the graph, the response of this RC circuit to a step input. And the current follows this exponential decaying curve. And you need to remember this curve, not the solution to the differential equation. So we see here for the RC charging circuit at various values, various fractions or multiples of the time constant, we see what the RC value is at T is equal to tau. Tau is equal to R times C. And the voltage is 63.2% of its maximum value. And the current is 36.8% of its maximum value, or 63.2% of its way towards its final value, which is essentially zero. So this table just shows values from the curve on the previous slide. Now let's consider an RC discharging circuit where the capacitor is fully charged and then the voltage supply is replaced by a short circuit, and at time t equals 0, the switch is closed. What will happen is that the voltage across the capacitor will start out at V supply, the voltage it was charged to, and then it will decay to 0. And in one time constant, it decays 63% to 37% of the initial value. And in 5 time constants, it is fully discharged. And here is a plot of the current, capacitor discharging current. The time constant is still R times C. The equation that describes this exponential decay is given here. Where does this come from? If you write Kirchhoff's voltage law for this circuit, it says that the sum of the voltages around a closed loop is equal to 0. I only have 2 voltages, the voltage from the charged capacitor and the voltage drop across the resistor, VC plus IR equals 0. But again, I know for a capacitor, the constitutive equation for it is that the current is equal to the capacitance times the time rate of change of the voltage across the capacitor. So if I substitute this in for I and carry down the R, I get this equation. I reorganize terms and I get this equation. And again, I could transform this into an algebraic equation and could plot the voltage versus time, current versus time curves. Mathematically, the solution to this equation, given an initial condition at time t equals 0, Vc is equal to the supply voltage, Vs, the solution is given by this expression. And for the discharging circuit, the RC discharging circuit, similarly, I have various fractions or multiples of the time constant and the corresponding RC values where the time constant is RC. So when t equals tau, tau is equal to R times C. I see that the voltage for the discharging circuit is 36.6% of the maximum value, and the current is 63.4% of the maximum value. Now here we see the response of my RC circuit to a square wave input. If I input a square wave, and the square wave has a period of 10 time constants, meaning that it goes up, over, down, over, and this is one then cycle. And the period of that cycle is twice 5 tau, or 10 tau. So if the period is 10 tau, then in half of that period, the capacitor will charge, and it will charge fully, and then it will discharge fully. So you see the response, charging, discharging. So as long as I give the capacitor time to fully charge and then discharge by making the period of the square wave no less than 10 tau, I will get full response. If, however, I increase the period, make it 8 tau, or rather 16 tau, 8 tau is half the period, we see that the response will get to steady state, and then it will stay there from 5 tau to 8 tau. And then it will discharge, and then it will stay there until 16 tau. And then it will repeat. However, if I make the period less than 10 tau, say 8 tau, or half of the period to be 4 times tau, the time constant, I see that the capacitor will not fully charge because in 4 time constants, it does not get up to its steady state value. And then because the square wave reverses, it will then discharge. And the same thing will apply. Charge, discharge, but never fully charge or fully discharge. When we input a sine wave to a linear dynamic system, the output is also a sine wave. Same frequency, different amplitude, and with a phase shift. If I plot the amplitude ratio, output over input, versus frequency, and the phase angle versus frequency, I get what I call the Bode plots, or frequency response plots. So as we will learn over and over again, for this RC circuit, which is a first order dynamic system, its frequency response looks like this. It is flat until it gets to what we call the bandwidth, which is 1 over the time constant, tau. At that point, the amplitude is dropped minus 3 dB from the low frequency or DC value, and then it rolls off in a straight line at a slope of minus 20 dB per decade, where a decade is a 10-to-1 frequency change. For example, from 10 to the first to 10 to the second is a decade. From 10 to the 0 to 10 to the first is a decade. Now, S is the same as D, the differential operator. D, or S, means take the derivative. 1 over D, or 1 over S, means take the integral. So I see if I look at the frequency response of a pure integrator, it's given by this straight line here. And I see that at high frequency, the RC circuit and the integrator are identical in behavior. So if I look at the frequency 10 times greater than the bandwidth, I see that my RC circuit behaves like an integrator. Similarly, if I look at the CR circuit, the CR circuit is a high-pass filter. And we see that its frequency response has a slope of positive 20 dB per decade up until the bandwidth, which is 1 over tau in radians per second. And then it flattens out at, in this case, 0 dB. So at the bandwidth, which is 1 over the time constant, in radians per second, the amplitude is minus 3 dB, of the steady state value, which is 0 dB, or the constant value at high frequency. Now, S is like D, means take the derivative. The frequency response of S, a differentiator, a derivative, is shown by this straight line. And we see that at low frequency, at 1/10 of the bandwidth and below, the CR filter and the differentiator, the frequency response plots, are identical. So what we then take away from this is that at frequencies 10 times greater than the bandwidth of an RC circuit, and the bandwidth is 1 over tau, where tau is the time constant, R times C, the RC circuit behaves like an integrator. At frequencies 1/10 of the bandwidth and below, where the bandwidth is 1 over tau in radians per second, where tau is R times C. At frequencies 1/10 of the bandwidth and below, the CR circuit behaves like a differentiator. Here we see our RC integrator. The RC circuit behaves like an integrator when the frequency that I'm dealing with is 10 times greater than the bandwidth. So at high frequencies, the integration of a square wave is a triangle wave. The integration of a constant is a ramp. And I see that this relationship, the integration, holds at high frequencies and does not hold at medium frequencies or at low frequencies. The RC integrator behaves, the RC circuit behaves as an integrator at high frequencies, at frequencies 10 times greater than the bandwidth and above. Here I have my CR circuit, and the CR circuit behaves as a differentiator for frequencies 1/10 of the bandwidth and below. The bandwidth is 1 over tau in radians per second, and tau is R times C. So at low frequencies, when I input a square wave at a frequency below 1/10 of the bandwidth, the derivative of the square wave, or the step, is an impulse, and I see the impulse response. I do not see that at medium frequencies or at high frequencies because the CR circuit does not behave as a differentiator except at low frequencies. Here is an example using Simulink. If I have a square wave into my RC circuit transfer function, remember S is the same as the differential operator D, and here I've made tau equal to 1. So at a frequency 10 times the bandwidth, and the bandwidth is 1 over tau, or 1 radian per second. At frequencies 10 times that and above, if I input a square wave, the integral of a square wave will be a triangle wave. And I see that happening here. square wave input, triangle wave output. For the CR circuit, if I make the input signal square wave, 1/10 of the bandwidth, where the bandwidth is 1 over tau in radians per second, and tau here is 1, I see that my square wave is shown, the square wave input, and the derivative of the square wave is an impulse. Square wave input in, impulse wave out. We will now perform a complete dynamic system investigation of this first order dynamic system, the RC circuit. We see I've shown the RC circuit with the two input variables whose product is power, voltage and current, and the two output variables whose product is power, voltage and current. I need to express the relationships between the input voltage and current and the output voltage and current to have a complete dynamic description of this RC circuit. First, I create a physical model of this RC circuit. And the first step is to use engineering judgment and apply simplifying assumptions. I will assume the resistors and capacitors are pure, only have the attribute for which they are named, and ideal, meaning linear. The voltage sources are ideal and supply the intended voltage to the circuit, no matter how much current, and thus power, this might require. And the measuring devices are ideal and do not load the circuits by drawing any current. So now I've reduced my physical system to this physical model where R and C are pure and ideal. E in is an ideal voltage source. E out is measured using an ideal measuring device because I assume that I out is equal to 0. As part of my physical model creation, after I make simplifying assumptions using engineering judgment, and I have my physical model, I need to identify parameters in my physical model. We call that model parameter identification. I'll measure the resistor and capacitor components using a digital multimeter, and I'll note tolerances. I find that the resistance value is 15 kiloohms nominal with 5% tolerance, and I actually measure 14.986 kiloohms. The capacitor has a capacitance of 0.01 microfarads nominal, and I measure 0.00985 microfarads. The mathematical modeling of my physical model is next. I'll start by creating the complete mathematical model of my RC circuit with the input variables voltage and current, whose product is power, and the output variables voltage and current, whose product is power. If I apply Kirchhoff's voltage law and Kirchhoff's current law, along with the constitutive equations for the capacitor and resistor, I can get this matrix representation, where D is the differential operator. And what this says is that E in equals RCD plus 1 times E out minus R times I out. I in equals CD times E out minus 1 times I out. Then if I want the relationship between input and output versus output and input, I see that E out equals 1 times E in minus R times I in. I out is equal to CD times E in minus the term RCD plus 1 times I in. Make sure that using Kirchhoff's voltage law and Kirchhoff's current law, along with the constitutive equations for a capacitor and for a resistor, you can verify that these equations are correct. This is the complete mathematical model. Now for us, we are assuming I out is 0. So here you see basic components R and C equations, which are the constitutive equations. For a resistor, it says E in minus E out, or the voltage drop across the resistor, is equal to the current flowing through the resistor times the resistance. And for the capacitor, the current flowing through the capacitor, which we know doesn't really exist, it's around the circuitry, it's through the circuitry around the capacitor. This current is equal to the capacitance times the time rate of change of this output voltage, the voltage across the capacitor. And IR equals IC because we're assuming I out is equal to 0, meaning that this RC circuit is not connected to anything downstream that will draw current. Kirchhoff's current law is then at this node, IR equals IC plus I out, but I out is 0. IR equals IC. IR is the voltage drop across the resistor divided by the resistance. And IC is equal to C times DE out dt. If I rewrite this equation, I get this first order, linear, constant coefficient, ordinary differential equation. If I define RC as tau, and even though the coefficient of E in is 1, I'll generalize and say it's equal to K. And in this case, K is equal to 1. The general form of my equation is given here. Now, once I learn everything there is to know about this equation, I will discover that there are many, many different physical systems whose physical models have, as a mathematical model, this equation. So once I've solved this, I only need to do it once, and it will apply in many, many different physical situations. Now, a preferred approach to getting that transfer function or differential equation is to recognize that I have a voltage divider, since the current at this node going out is 0. If I replace the resistance by its impedance, which is R, capacitor by its impedance, which is 1 over CD, and I just use my voltage divider expression, E out is equal to E in times 1 over CD divided by R plus 1 over CD. If I simplify, I get 1 over RCD plus 1, which I call my transfer function. And again here, I'm using the fact that my impedance for the resistor is R. The impedance for the capacitor is 1 over CD. Once I have the transfer function, I can get the differential equation, if I desire it, by just cross-multiplying. RCD plus 1 times E out equals 1 times E in. Then I distribute RCD times E out plus 1 times E out equals 1 times E in. D times E out means take the derivative. RC dE out dt plus E out equals E in, which is the differential equation I derived using Kirchhoff's current law. Let's say a few words about linear time invariant behavior versus non-linear time invariant behavior. Linear time invariant systems, LTI systems, are what we assume our systems to be, although that is the exception. Most real-world systems are non-linear time invariant systems. A linear time invariant system is one that is linear and time invariant, as the words describe. A frequency domain transfer function is limited to describing elements that are linear and time invariant. And these are severe restrictions, as I just said. No real-world system meets them. Linear time invariant system properties are homogeneity. If I have an input, I get an output. If I multiply the input by a constant, the output gets multiplied by the same constant. Superposition. If I have an input, I get an output. A different input, a different output. Both inputs at the same time, both outputs added together is the total output for my system. Time invariance. If I apply an input at time t, I get an output at time t. If I apply an input at some later time, t minus t1, the input then appears at time t minus t1. Time invariance. Transfer functions. The basis of classical control theory, which we will spend quite a bit of time on in this course, require LTI, linear time invariant systems. But no real-world system is completely LTI. There are regions of nonlinear operation and often significant parameter variation. Examples of linear behavior are addition, subtraction, scaling by a fixed constant, integration, differentiation, time delay, and sampling. No practical control system is completely linear, and most vary over time. LTI systems can be represented completely in the frequency domain. Non-LTI systems can have frequency response plots. However, these plots change depending on system operating conditions. Let's look at the analytical solution to this first-order linear constant coefficient ordinary differential equation. I'm doing this only to be complete and thorough, to review what you've learned in the past. But let me make the point that we will not be solving differential equations. MATLAB and Simulink will do that for us numerically. However, in terms of step response and frequency response, what's important are not the mathematical expressions, but the graphs, the pictures, what the graphs tell us, how that relates to applications. That is essential. That is what we will emphasize going forward. but let me cover this for completeness. The classical operator method of solution is a three-step procedure. Find the complementary or homogeneous solution for the equation with the input equal to 0. Find the particular solution with the input present. Get the complete solution. That is, sum of the complementary and particular solutions, and evaluate the constants of integration in the complementary solution by applying known initial conditions. Step 1, set the input equal to 0. We take our differential equation, we use the differential operator, we transform it to an algebraic equation in the differential operator d. And in MATLAB Simulink, d is represented by the variable s, which s comes from the Laplace transform method of solving differential equations. We let E in be 0, and so then the equation that results is tau d plus 1 equals 0. This is called the characteristic equation of this differential equation. We solve for d. The solution, the complementary solution, is equal to some constant times e to the d times time. So the complementary solution is E out complementary is some constant C1, which we will get from the complete solution using the initial condition, C1e to the minus t over tau, where in this case tau is the time constant, and physically it's the product of resistance times capacitance. But mathematically, it's the time constant. And for different physical systems, it will represent different physical parameters. So we only need to solve this equation once. So E out complementary is C1e to the minus t over tau. Constant C1 is determined from the initial condition once the complete solution is formed. Step 2 of the process, for a step input, En is a constant. So I assume my particular solution is a constant, C2. I substitute that into my differential equation, and I see that the derivative of the constant is 0. E out particular is C2. C2 equals K times E in. So E out particular equals K times E in. K is part of my differential equation. It's a parameter along with tau in my mathematical model. Step 3, combine the complementary solution with the particular solution, which we do here. To solve for C1, I apply the initial condition. At time t equals 0, E out equals 0, which leads to C1 given by this expression. The complete solution then is given by this expression. And I can see that when t is equal to tau, this becomes 1 minus e to the minus 1, which is 0.632. The steady state value for E out is K times E in. And at t equal to tau, the solution is 63% of the way to steady state. If I now consider the input to my first order dynamic system to be a sine wave, then the result is what we call frequency response. And the plots that we obtain are called Bode plots. If I assume that the input to the system is A sine omega t, omega is the frequency in radians per second. Since this is a linear mathematical model for a linear physical model, when I input a sine wave into a linear system, I get a sine wave out, same frequency, an amplitude that varies with frequency, and a phase angle that varies with frequency. And this is all in the steady state after the transient response has died away. So I assume that the particular solution is some constant times A sine omega t plus a phase angle. I then have to substitute this into my differential equation, which means I have to take the derivative of this particular solution, substitute in the particular solution, and then solve for phi and C2, which I will see are functions of omega. So the mathematics that follows in the next 2 slides is accomplishing that task, solving for C2 and phi, which I will discover are functions of frequency. So after substitution, I follow these steps, and I'll leave it to you to follow through the mathematics. That's not what's important here. What's important here is the result, and most importantly are the Bode plots that we see for a first order linear constant coefficient ordinary differential equation, a linear mathematical model of a first order system. So the mathematics leads then to 2 equations with 2 unknowns, phi and C2. And I can solve these mathematically using a technique known as Cramer's rule. But let's just leave it at that and just leave the mathematics as a side issue or something that you can investigate on your own. The result of the analysis is that the tangent of the phase angle is minus tau times omega, and C2 is given by this expression. So in the steady state, if the input to my first order dynamic system mathematical model is A sine omega t, the particular solution, the output, is C2A sine omega t plus phi, where the tangent of phi is minus tau omega, and C2 is given by that expression. Frequency response, which is what we've just performed, is the steady state response of the system to an input sine wave at a particular frequency. If the input is A sine omega t, the output is C2A sine omega t plus phi, where the tangent of phi is minus tau omega, and C2 is given by this expression. The complementary solution will decay to 0 with time. The particular solution is the steady state solution. The input is a sine wave, and the steady state output is a sine wave with the same frequency, but with a frequency-dependent amplitude and a frequency-dependent phase angle. Let's take our first order system mathematical model, tau d E out dt plus E out equals k times E in. Even though we're using E for voltage, this first order mathematical model can represent many types of physical systems. Once we solve the mathematical equation once for step response and frequency response, we're done. We never have to do it again. We just have to know what tau and k represent physically. For an RC circuit, tau is R times C, and K is 1. For a mechanical system, a thermal system, any other disciplinary system, K and tau will have other physical meanings. But mathematically, the solution to the equation, step response and frequency response, are the same. So let's create a Simulink block diagram for this first order system. The procedure is step 1, solve for the highest derivative. dE out dt equals 1 over tau times ke in minus E out. Step 2, create the stem. This is the derivative of E out with respect to time. We integrate once with an initial condition on E out, and we get E out. That's the stem. Step 3, do what the equation says. dE out dt equals 1 over tau, a gain block, times the sum of k times E in minus 1 times E out. Step 4, write the equation from the block diagram. And it's very simple to do. dE out dt equals 1 over tau times this arrow, which is the sum of K times the external voltage E in minus 1 times E out. And that's my equation. The block diagram represents the equation, the mathematical model. Let's talk for a minute about plotting numerical data. Engineers are well known for their ability to plot many curves of experimental data and to extract all sorts of significant facts from these curves. The better one understands the physical phenomena involved in a certain experiment, the better is one able to extract a wide variety of information from graphical displays of experimental data. Understand the physical processes behind the data. When data may be approximated by a straight line, the analytical relation is easy to obtain. But when almost any other functional variation, for example, exponential, polynomial, complex logarithmic, is present, difficulties are usually encountered. It is convenient to try to plot data in such a form that a straight line will be obtained for certain types of functional relationships. Let's see how that might work in our situation. Here is my first order ordinary differential equation. I know the solution is given by this expression. Let's work with this equation. If I take both sides and I divide by ke in, I then get this equation here. If I then rewrite it so that on one side I have e to the minus t over tau, this equation results. I find a common denominator for this term, and then this equation results. If I then raise both sides of the equation to the minus 1 power, then this equation results. This gets inverted, this side gets inverted, and the minus sign disappears from the exponent here. So here is the equation that I have now arrived at. Ke in over Ke in minus E out equals e to the t over tau. If I take the log to the base 10 of both sides of the equation, then the log of e to the power is equal to the power times the log to the base 10 of e. That's a rule of logarithms. So now, if I then factor out the t from the right side, I get 1 over tau log to the base 10 of e, which is a number. It's a number, times time, which is a variable. And I plot the log to the base 10 of this quantity, where E out is what is varying. I then see that I have a straight line. This is simply y equals mx. This is y, x is time, this is the slope, 1 over tau log to the base 10 of e. The point here is that this approach gives a more accurate value of tau, since the best line through all the data points is used rather than just 2 points, as in the 63.2% method. In other words, finding out where, at what time, the amplitude is 63.2% of the final value. Furthermore, if the data points fall nearly on a straight line, we are assured that the instrument is behaving as a first-order type. If the data deviate considerably from a straight line, we know the system is not truly first order, and a tau value obtained by the 63.2% method would be quite misleading. An even stronger verification or refutation of first-order dynamic characteristics is available from frequency response testing. As we will see, if the system is truly first order, the amplitude ratio follows the typical low and high frequency asymptotes. Slope of 0 at low frequency, minus 20 dB per decade at high frequency, and the phase angle approaches minus 90 degrees asymptotically. If these characteristics are present, the numerical value of tau is found by determining omega, radians per second, at the breakpoint, and using tau equal to 1 over omega breakpoint. And the breakpoint is the point where the amplitude ratio drops minus 3 dB, or 0.707 of the low frequency value. Deviations from the above amplitude and or phase characteristics indicate non-first order behavior. What is the relationship between the unit step response and the unit ramp response, and between the unit impulse response and the unit step response? For a linear time invariant system, the response to the derivative of an input signal can be obtained by differentiating the response of the system to the original signal. For a linear time invariant system, the response to the integral of an input signal can be obtained by integrating the response of the system to the original signal, and by determining the integration constants from the zero output initial condition. The unit step input is the derivative of the unit ramp input. The unit impulse input is the derivative of the unit step input. Once you know the unit step response, take the derivative to get the unit impulse response, and integrate to get the unit ramp response. We might also want to understand how this equation can be solved numerically. Here's my mathematical model. Well, we use a numerical approximation. So our equation is tau times dE out dt plus E out equals K times E in. Well, the derivative is just the change in E out over the change in time as delta t approaches 0. So tau times this ratio plus E out equals K times E in. I can solve for delta E out using algebra. The algorithm, or the steps for solving this equation, are as follows. Step 1, initialize variables. Tau, E in, the start time, which is 0, the end time, delta t, the step, the incremental change in time, and E out, the initial condition. Step 2, increment time and stop when done. The new time is equal to the old time plus delta t. If t is equal to t end, then stop. Step 3, compute E in. Step 4, solve. Delta E out equals 1 over tau times K E in minus E out times delta t. Determine the new E out. E out new equals E out old plus delta E out, which we just solved for. Step 6, go back to step 2. So let's look now at the mathematical analysis and prediction for step response and frequency response, focusing on the graphical presentations of the responses. Here's our mathematical model. Here's our mathematical model in terms of the differential operator. I then factor out E out on the left-hand side of the equation. I then solve for the ratio of E out over E in, which is my transfer function. In general form, RC is tau, 1 is K. K is called the steady state gain, tau is called the time constant. The response, the step response, looks like this curve. At t equal tau seconds, in this case R times C, the response is 63% of the steady state value, which in this case is 1. And this is for a value of R equal to 15 kiloohms and C equal to 0.01 microfarads, which if multiplied together will give me 0.15 milliseconds. This is the response you want to remember. And at 5 time constants, you're at steady state, or over 99% of the way to steady state, which from an engineering point of view is steady state. Some definitions. The time constant tau is the time it takes the step response to reach 63% of the steady state value, K times E in. Rise time is 2.2 times tau. That's the time it takes the step response to go from 10% to 90% of the steady state value, K E in. Delay time, T sub D, that equals 0.69 times tau. That's the time it takes the step response to reach 50% of the steady state value, which is K E in. The steady state value of the response is K E in, and at 4 tau seconds, 4 time constants, the response has reached 98% of the steady state value. For all practical purposes, this is steady state. Well, 5 time constants will get you to over 99% of the way to the steady state value. So either 4 time constants or 5 time constants are typically used to represent steady state. Many of you are not familiar with semi-log paper. And by log, I mean log to the base 10. Log of a number is the power that 10 must be raised to give you that number. If I consider along the bottom axis that these numbers represent a decade, so let's assume that this 1 represents 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. If I wanted to plot the log of those numbers, the log of 10 is 1. At the top, I have a linear scale. So the log of 10 is 1. The log of 20 is 1.301, which is right here. The log of 30 is 1.477, which is right here on the linear scale. The log of 40 is 1.602, which is right here on the linear scale. The log of 50 is 1.699, right here on the linear scale. The log of 60 is 1.778, right here on the linear scale. The log of 70 is 1.845, plotted right here on the linear scale. The log of 80, 1.903, right here on the linear scale. The log of 90, 1.954, plotted right here on the linear scale. And the log of 100 is 2. 10 squared equals 100. So if I wanted to take the numbers 10 through 100 and plot the log to the base 10 of those numbers, I could do it on a linear scale, or equivalently, I can let the semi-log paper, this is a logarithmic scale in the horizontal axis, take the logarithm for me. So on the logarithmic paper, this is 10, this is 20, this is 30, 40, 50, 60, 70, 80, 90, 100. And these represent the log to the base 10 of those numbers. So I'm plotting the log to the base 10 of those numbers, but I'm letting the paper take the logarithm for me, rather than plotting on a linear scale and having to actually, with my calculator, take the log to the base 10 of those numbers. Let's talk about frequency response. For a linear system, if I input a sine wave at some frequency, the output will be a sine wave. Same frequency, has to be. Different amplitude, where the amplitude depends on frequency, and a phase angle, where the phase angle depends on frequency. So if I were to input a sine wave at varying frequencies, wait for the transient response to die away, so I'm just looking at the steady state response, and I did that for a whole range of frequencies and plotted amplitude ratio, output over input, and phase angle, those two data points for each frequency, I would obtain what we call the frequency response plots, or the Bode plots. And I see if I plot those results on semi-log scales, where the horizontal axis is logarithmic to the base 10, and that's my frequency in hertz. And in the magnitude scale, the vertical axis, the magnitude, the amplitude ratio, output over input, is determined by dB, decibel, where the value in dB is obtained by multiplying 20 by the log to the base 10 of the number that we want to convert to dB. This is the amplitude ratio in dB. This is the frequency in hertz. This is the phase angle in degrees. This is the frequency in hertz. And the horizontal axis is a logarithmic scale to the base 10. The curve for a first-order linear system looks like this. It is flat, and at the bandwidth, which is 1 over tau, 1 over RC, in this case, 6,666.7 radians per second, which is 1061 hertz, the amplitude is dropped minus 3 dB from the low frequency value. In this case, K is 1. 1 in dB is 0. And then the slope of this line is minus 20 dB per decade. And the phase angle goes from 0 to minus 45 degrees at the bandwidth to minus 90 degrees at very high frequency. This is what you need to remember. The picture of the Bode plots, the frequency response plots, for a first-order linear dynamic system. In particular, the low-frequency slope, the high-frequency slope, the bandwidth, the value of the amplitude ratio at the bandwidth, the low-frequency phase angle, the high-frequency phase angle, and the phase angle at the bandwidth. In the time domain, if I input a sine wave at the bandwidth, 1061 hertz, which you see here in the blue curve, I wait for all the transients to die away, and I look at the steady state response, the Bode plots tell me that the amplitude of the output sine wave will be 0.707 of the amplitude of the input sine wave. The sine waves will have the same frequency, and the output will lag the input by 45 degrees. The phase angle is minus 45 degrees. Bandwidth. We've used the term. Let's formally define it. The bandwidth is the frequency where the amplitude ratio drops by a factor of 0.707 or minus 3 dB of its gain at zero or low frequency. For a first-order system, the bandwidth is equal to 1 over tau. It's a measure of the speed of response of the system. The larger the bandwidth, the faster the step response. Because 1 over tau, if 1 over tau is large, tau is small. Tau is the time it takes to get to 63% of the steady state value. Small tau, fast response. Small tau, large bandwidth. So the smaller the bandwidth, the slower the step response. But bandwidth is also a direct measure of system susceptibility to noise, as well as an indicator of the system's speed of response. Note that the amplitude ratio follows low and high frequency asymptotes, slope 0 at low frequency, minus 20 dB per decade at high frequency, and the phase angle approaches minus 90 degrees asymptotically at high frequency. Starts off at 0 degrees at low frequency. And at the break frequency, the bandwidth, 1 over tau, phase angle is exactly minus 45 degrees. So if you have a frequency response plot and the frequency response, the Bode plots, have these characteristics, you then have a first order dynamic system. Whereas the step response may not be definitive in identifying the nature of the system, because many systems of different orders have similar step responses. But that's not true of the frequency response. That's why we call the frequency response the gold standard for system identification. Here we have a diagram that shows the Bode plotting of first order frequency response. And it just shows you how we convert numbers to dB. So 0 dB is 1, a half is minus 6 dB, a tenth is minus 20 dB, a hundredth is minus 40 dB. If we double the value, we go up 6 dB. Multiply by 10, it's 20 dB, 100, 40 dB. And again, dB is the 20, it's 20 times the log to the base 10 of the amplitude ratio. A decade is a 10-to-1 frequency change. An octave is a 2-to-1 frequency change. And we show here, if my transfer function is 1 over tau s plus 1, my Bode plot looks like this. Starts out flat, bends, and approaches minus 20 dB per decade in slope, starts at 0 degrees, goes through minus 45 degrees at 1 over tau the bandwidth, and then approaches minus 90 degrees. If we're looking at the Bode plot for simply tau s plus 1, then it starts out flat, goes to plus 3 dB at the bandwidth, and then approaches at high frequency the slope of plus 20 dB per decade. And the phase angle starts at 0, goes to 45 degrees, plus 45 degrees at the bandwidth, and plus 90 degrees at large frequency. Computer simulation without experimental verification is at best questionable and at worst useless. So our predictions need to be verified by measurements. Let's look at our RC circuit and measure the time response, that's a step input, and the frequency response, that's a sine input. So here I have the step response. I have a square wave input. The sign of an accomplished engineer is being able to set the parameters of the measuring instruments before actually making the measurement, and not simply turning the measuring instrument on and then seeing garbage on the screen and trying to turn the dials so something that makes sense appears on the screen. You might as well wear a sign saying, I don't know what I'm doing. So you want to be able to predict what you will measure and then set the dials of the measuring instrument, in this case the oscilloscope, so that when you actually hook up your system to the measuring instrument, what you expect to appear appears. So the question is, why do I pick for my waveform generator a square wave at 500 Hertz? Well, very simply, if I know my time constant is 0.15 milliseconds, and in 5 time constants, I'm 99% of the way to the steady state value, and that's 0.75 milliseconds, well, just so I give my system time to stay at steady state, I'll just use 1 millisecond. And since the period of my square wave will be twice that, I'll pick the period to be 2 milliseconds. So a square wave frequency, 1 over 2 milliseconds, is 500 Hertz. So if I pick 500 Hertz, you see that my step response in 5 time constants gets to steady state, but then it stays at steady state for a bit before the square wave reverses and my response goes in the other direction. Here I zoom in on the step response, and I see that at 63%, the delta t is 118 microseconds, or 0.118 milliseconds. I expect to see 0.148 milliseconds, as that is what the product of R times C for my actual parameter values is. Here, I'm using from National Instruments a virtual instrument from the MyDAC data acquisition device, rather than a desktop digital oscilloscope. That could be a reason for the inaccuracy in my measurement. Now, what does this Bode plot physically mean? Well, what it shows me is that if I input a sine wave at a certain frequency, I get a sine wave out, same frequency, but as I increase the frequency, the amplitude ratio will get smaller, and the phase angle will go from 0 degrees to minus 90 degrees. So I see at 100 hertz, the two sine waves are almost identical. 400 hertz, I get an attenuation, a reduction in amplitude slightly, with a slight negative phase angle. 800 hertz, the amplitude reduction is greater, the phase angle, negative phase angle is greater. At 1061 hertz, which is the bandwidth, I expect that the amplitude ratio to be 0.707 and the phase angle to be minus 45 degrees. Here I show the amplitude ratio to be 0.798 and the phase angle to be minus 40.5 degrees. So on these measurements, clearly something is incorrect. Either in making these measurements, I changed the values of R and C, so 1061 hertz is not the actual bandwidth, and comes from the nominal value, and the actual values of R and C might be slightly different than the ones I originally measured. In any case, it's the process, the procedure that's important, not the actual values here that I'm presenting to you. Then as I increase the frequency, you see that the amplitude ratio gets smaller and smaller, and the phase angle gets larger and larger in a negative value. But it'll never get, the phase angle will never go past minus 90 degrees. However, the amplitude ratio will continue to get smaller and smaller. So you see 1300 hertz, 1800 hertz, 2500 hertz, 4000, 10,000. You can see here at 10,000 hertz, 10K hertz, the amplitude ratio, very, very small, 0.156. The phase angle is 79.2 degrees. And the way I know that is because if I look at the delta t between the peak of one curve and the peak of the other curve, and I know what the delta t is, which is 22 microseconds, and I know the frequency of the sine wave is 10 kilohertz, I can then take this delta t, divide by the period of the sine wave, multiply by 360 degrees, and get 79.2 degrees. Here is the Bodie plot from the MyDAC. Now, this is a particularly useful virtual instrument, the Bodie plotter, because to do this manually would take quite a bit of time, as for each data point shown, I would have to input a sine wave from my waveform generator into my RC circuit, look at the steady state output sine wave, calculate the amplitude ratio, convert it to dB, and plot it. Compare the two sine waves, determine the phase angle, and plot it. And do this for each frequency represented by the dots on this curve. So this might take an hour to do. With the MyDAC Bodie plotter, which is a virtual instrument which you will be using in the National Instruments device MyDAC, this is done automatically in a matter of seconds. There are such things as dynamic signal analyzers available as there are digital oscilloscopes, but while an oscilloscope might cost a few $1,000s, a dynamic signal analyzer costs $25,000. So this virtual Bodie plotter is very, very useful and time-saving. Let's look at the analogy of our RC electrical system with a mechanical system. We know that the mechanical analog for a resistor is a damper. The resistance is analogous to the viscous damping coefficient. The capacitance is analogous to a spring, where C and 1 over K are analogous. Voltage is analogous to force. Current is analogous to velocity. So if I assume there's no output current from my RC circuit, the current through the resistor and capacitor are the same. Therefore, the velocity of the damper and the spring must be the same. So the end motion of the spring and the damper must be the same. They must have the same velocity. This is my voltage input. This is my force input. What I measure is the voltage across the capacitor. What I measure in the mechanical system is the force of the spring. On the electrical system, if I use Kirchhoff's voltage law, and say E in minus the voltage drop across the resistor minus the voltage drop across the capacitor equals 0. E in minus the voltage drop across the resistor is I times R, minus the voltage drop across the capacitor is E out. I replace I using the constitutive equation for the capacitor. The current flowing through the capacitor is C times dE out dt. I then carry down the R. I rewrite my equation, and I have my first order ordinary differential equation, which we've already looked at several times and are familiar with. Using the differential operator d, I have my transfer function, and tau, the time constant, is R times C. Now, if I just went over laterally to the mechanical system, I could write down just by inspection what the differential equation is and what the transfer function is for our mechanical analog. Since R is the same as B, C is the same as 1 over K, E out is F out, and so this is the derivative of F out with respect to time, F out dot. E out is F out, E in is F in. The ratio of F out to F in force out to force in is the same as the ratio of E out to E in, which is 1 over R is B, C is 1 over K, D plus 1, tau is R times C, tau is B over K. If I come back to the actual mechanical system, I can say that the summation of forces is equal to 0, where the forces are the input force, and the force of the damper, and the force of the spring. And that equals 0. Summation of forces equals 0. There is no mass here. So there's no inertia force, mass times acceleration. The damping force is B times the velocity of the end of the damper, since one end of the damper is connected to ground. The spring force is K times X, where X is the displacement of one end of the spring, where the other end of the spring is connected to ground. But K times X is my output force. That's what I want to measure. So F in minus B times V minus F out equals 0, or F in minus B times F out dot over K minus F out equals 0. Because velocity, since F out is K times X, and F dot is K times V, F out dot is K times V. And so V is equal to F out dot divided by K. Again, the damping force is B times V. The spring force is K times X, and that's F out. If I take the derivative of that output force, I get F out dot equals K times X dot, or K times V. V is then F out dot divided by K, which I've substituted here. So then if I rewrite that equation, I get the mechanical analog as we've already discussed. So that concludes our discussion of RC systems, both RC and CR network systems. Thank you for your attention.